Hey guys, today we're gonna talk about phyllosilicates. But before I start on the topic, let me remind you the topics that we discussed previously in the classes before COVID-19 situation. So actually, these are the main topic is was the silicates. So silicates are basically divided into six different categories or the subclasses. Um, Mesosilicates, sorosilicates, ionosilicates, cyclosilicates, phyllosilicates that we are going to discuss today, and then tectosilicates. They are also known as mesosilicates are known as single tetrahedrons, then the sorosilicates double tetrahedrons, ionosilicates are known as single and double chance tetrahedrons, then cyclosilicates or ring silicates. Then the phyllosilicates are also known as sheet silicates. Tectosilicates are known as 3D framework silicates or just simply framework silicates. Okay, so phyllosilicates. Let's start with this. So phyllosilicates are, as I told you earlier, are also known as sheet silicates. These are very important group of minerals that includes the micas, chlorides, serpentine, talc, and the clay minerals. Many members have a platy or flaky habit with one very prominent cleavage. That's why you can that's why you can take the flags out of them. They have got a unidirectional cleavage, means in a single direction. So cleavage, as you know, is a tendency of a mineral where it can be broken easily. It can break easily. So these minerals are generally soft, have very low specific gravity, may even be flexible. Most are hydroxyl bearing. Let's talk about structure. So the basic structure of the phyllosilicates is based on interconnected six-member rings of SiO4 tetrahedra that extend outward in infinite sheets. Three out of the four oxygens from each tetrahedra are shared with other tetrahedra. This leads to a basic structural unit of Si2O5. Now let me describe it here in this diagram. Now take these two tetrahedrons. Actually, this is the single tetrahedron and this is another one. Now because the formula says silicon, there are two atoms of silicon, so these are actually oxygen atoms and this is also oxygen. In behind this oxygen atom, there's a silicon atom which is not shown here, but you can visualize that there are two silicon atoms which are surrounded by 8 oxygen atoms, or for each tetrahedron 4 oxygen atoms, 1, 2, 3 and 4. Now if you count the number of atoms of silicon, these are 2, and if you count the number of shared oxygen atoms, these are 5. So let me tell you how. This is one which is shared, second one is also shared, third one is also shared, fourth one is also shared, and fifth one is also shared. These two are free. They are not shared with any other tetrahedron. So here comes the formula. Okay, so this word phyllosilicates actually comes from a Greek word phyllon, which means leaf. Why this leaf? Because it has got the structure or the arrangement of this silicon and oxygen atoms is kind of a plate or flake or leaf-like. So phyllosilicates are the leaf-like platy or flaky minerals which have a layered structure. When you see mica, for example, which is a phyllosilicate, you can easily take off the kind of leaves or kind of the papers one upon one which are stacked on top of each other. They form parallel sheets of silicate tetrahedrons with SiO2 or a 2 to 5 ratio. That's what I discussed earlier, that 2 silicon atoms and 5 oxygen atoms. So this is the ratio 2 and 5. All phyllosilicate minerals are hydrated, either with water or with hydroxyl group attached with them. So now what is hydroxyl groups? This is actually, so the hydroxyl groups are alcohols. This is actually oxygen bonded to hydrogen. Now alcohols, for examples, could be ethanol, butanol, etc. If the organic compounds, which are often poorly soluble in water, they could become water soluble when they contain 2 or more hydroxyl groups. So the phyllosilicates or sheet silicates are an important group of minerals that include the micas, chlorides, serpentines, talc, and the clay minerals. These are abundant and common minerals throughout upper 20 km of crust. All are hydrous. They contain hydrogen bonded to oxygen to form OH or hydroxyl group. Each tetrahedra is bound to 3 neighboring tetrahedra via 3 basal bridging oxygens. That's what I explained in the diagram. Or let me take you to the previous slides. Okay, so they are attached. This upper side is not connected with any other tetrahedron. They are free, kind of free, not connected, not attached, but these basal sides are all connected. Clear? Okay. The apical oxygen of each tetrahedral in a sheet all point in the same direction. That's what you saw in the diagram. The sheets are stacked either a piece to piece or base to base. In an undistorted sheet, the hydroxyl group sits in the center and each outlined triangle is equivalent. Like this is the silicon tetrahedron and this one is the hydroxyl group. Okay, in the center are the hydroxyl group and the water molecules. Octahedral layers. Now apical oxygens plus the OH group coordinate a 6-fold octahedral site. 6-fold, you can see 1, 2, 3, 4, 5 and 6. These octahedral sites form infinity. These octahedral sites form infinitely extending sheets. I mean there would not be necessarily a limit to these sheets. All the octahedral lie on triangular faces oblique to the tetrahedral sheets that I will explain in the next diagram when we are discussing the minerals. The most common elements found in the 6-fold site are magnesium or iron or aluminium along with silicon and oxygen. So these are the common minerals which belong to phyllosilicates. You can see here, you might not be familiar with the names like serpentine, clays, micas, and chloride. This is the mineral group. Here are the different minerals representing that specific groups, and here are the chemical compositions. So let's first discuss serpentine subgroup. Serpentine subgroup. So this is definitely not a single mineral, but it's a name of a group, basically subgroup. So serpentine is a name used for large group of minerals that fit this generalized formula X223 Y2 O5 OH4. Let me describe this or explain this later on. The most obvious physical properties of serpentine are its green color, patterned appearance, and slippery feel. When you touch serpentine or any mineral from this group, it has got a oily or soapy feel. These remind the observer of a snake, and that is where the name serpentine was derived. Serpentine group minerals have similar physical properties and form by similar processes. Then they often occur as a fine grain, a mixture, and can be difficult to distinguish within a rock. Geologists usually call these materials serpentine rather than more specific names to simplify communication. Serpentine minerals form where peridotite, dunite, and other ultramafic rocks undergo hydrothermal metamorphism. Now, peridotite. What is peridotite? Now, what is peridotite? Peridotite is actually a dense, coarse-grained igneous rock consisting mostly of the minerals like olivine and pyroxene. This is an ultramafic rock as a rock contains less than 25% of silica. It is high in magnesium. You know, when any rock contains lesser amount of silicon, it the color of the rock gets darker and darker. So this rock contains less than 25% of silica, so it is high in magnesium, reflecting the high proportions of magnesium-rich olivine with appreciable amount of iron. Dunite. Now, dunite is also an igneous plutonic rock of ultramafic composition with coarse-grained or phaneretic texture. And other ultramafic rocks undergo hydrothermal metamorphism. Hydrothermal metamorphism, you must be aware or must be familiar with the term. Metamorphism is a process in which the rocks undergo enormous heat and pressure, due to which certain changes appear in the texture and in the structure of the rock. During hydrothermal metamorphism, olivine and pyroxene minerals are transformed into or replaced by serpentine minerals. Some of the metamorphic rocks produced here are composed almost entirely of serpentine minerals. These serpentine-rich rocks are known as serpentinites. Okay, so here the structure of the phyllosilicates. That's what I was talking previously that we will discuss later on. So these diagrams which are shown in blue and red are the silicon tetrahedron. This one is the, just visualize, is silicon, and these red um, balls are actually the oxygen atoms. Now these tetrahedrons, all the pyramid shape, are the silicon tetrahedron, and in the octahedral form in between them are the other atoms of magnesium, aluminium, maybe iron. So this is the layer of silicon. This is the layer of any other element, molecules. This again the layer of the silicon. So they are kind of stacked up. Okay, Okay, so they are kind of stacked up, one on the top of the other one. Here comes the colorful pictures of the common serpentine minerals. Now, these are the beautiful green color anticorite. So these are the common, there are so many serpentine minerals, but these three are the common ones: anticorite, chrysotile, and laserite. So this is anticorite, which is in crystal form here, then anticorite here in amorphous form. This one is chrysotile. Chrysotile, the variety that I have picked for you. This is the fibrous one. So these fibrous variety resembles, or this is a type of asbestos. This is laserite, the kind of pale or lime green color of the mineral. Now let's move to the next group of the minerals, clay minerals, which is very important group of minerals. The term clay is generally applied to a natural material with plastic properties. Clay has got particles of very, very fine size. So they are even less in size, lesser than 2 micrometers, and very fine material fragments or particles, composed mostly of hydrous layer silicates of aluminium, though occasionally containing magnesium and iron as well. So basically, clay minerals are hydrous aluminosilicates. Clay minerals are hydrous aluminium phyllosilicates, sometimes with variable amounts of iron, magnesium, alkali metals, etc. are found on or near some planetary surfaces. Clay minerals form in the presence of water. Clays form flake, as we discussed earlier, that this group is always this contains water or hydroxyl groups. So that's why clay minerals form in the presence of water. Clays form flat hexagonal sheets similar to the micas. Micas we will discuss later on. Clay minerals are common weathering products. Usually clay is the weathering product of feldspar, and they have very low resistance, and they could be um, weathered at very low temperatures. So clay minerals are very common in soils, in fine-grained sedimentary rocks such as shale, mudstone, and siltstone, and in fine-grained metamorphic slate and phyllite as well. So slate and phyllite are the metamorphic rocks. Clay minerals are usually ultra fine-grained. As I told you, even sometimes there's gas cannot pass through the pores because it has got porosity, but the pores are very, very fine, so they are not connected with each other, means no permeability. Clay minerals are usually ultra fine grain, normally considered to be less than 2 micrometers in size on standard particle size classifications, and so may require special analytical techniques for their identification and study. For example, the scanning electron microscope is used to study the internal structure of clays, or X-ray diffraction method is also used. Let's move to the next slide. Now, clay mineral group is divided into different minerals. This is halloysite, kaolinite, illite, montmorillonite, vermiculite, talc, sapiolite, paligorskite, pyrophyllite, to name a few. These are the pictures I have chosen for you to show you different types of clays, like this is halloysite, this is kaolinite, and few other types of clays. This is pyrophyllite, which has got kind of needle-like or structure. Now this is internal structure of vermiculite in particular, but I have chosen it for you guys to understand in general the structure of phyllosilicates. Now here, this is the index. This purple color is here, which is present here, is aluminium, and the yellow mustard color shows the silicon, green color shows the magnesium, then the lilac color shows the iron, grayish color shows titanium, and this rounded molecule is of hydrogen, the red color molecule is of oxygen, and this this not molecule, the atom of oxygen, and the green is calcium, then sodium and potassium and water. Now if you see here, this most prominent color in this diagram or in this picture is mustard, yellowish mustard color, which shows the silicon tetrahedron. Now you can see they are connected with each other and stacked up. Okay, this layer, the topmost layer is of silicon tetrahedron with some aluminium with them. This red color balls are oxygen which are surrounded and in between this silicon is surrounded by these four oxygen. The next layer is of magnesium tetrahedron or octahedral, whatever they may be. Then again this silicon tetrahedron are present in the next layer. In between these different types of layers sandwiched are the potassium, sodium, and water molecules. So this T represents this layer. The T represents again the same silicon layer, and O represents this magnesium rich layer. So this is the particular structure of vermiculite. Now what is vermiculite? Vermiculite is the type of the clay, this one. Okay, so this was in particular for vermiculite, but in general you can consider it for all the different types of clays. Let's move forward to mica group. Now mica, a group of hydrous potassium aluminum silicate minerals. What's the difference between mica and the previous one, clay minerals? The clay was hydrous aluminum silicates, whereas mica are hydrous aluminum but with the presence of potassium. So the difference is only potassium, that in the clay mineral potassium was negligible or not present, but in mica potassium is prominent. So these are the hydrous potassium aluminum silicate minerals. It's a type of phyllosilicates, of course, exhibiting a two-dimensional sheet or layer structure. Among the principal rock-forming minerals, micas are found in all three major varieties, either igneous, sedimentary, or metamorphic. So this is very common. The mica group of sheet silicates or phyllosilicate minerals includes several closely related materials having nearly perfect basal cleavage. All are monoclinic with a tendency towards pseudo-hexagonal crystals and are similar in chemical composition. The nearly perfect cleavage, which is the most prominent characteristic of micas, is explained by the hexagonal sheet-like arrangement of its atoms. As you can see here, this is kind of sheet-like arrangement of atoms. Mica is used in a variety of products, ranging from drywalls, paints, fillers, especially in parts for automobiles, roofing and shingles, electronics, etc. The word mica is derived from the Latin word mica, meaning a crumb, and probably influenced by micaire, it means to glitter. As you know, mica is glittery substance. It has got a glitter, a shine in it. The general formula for minerals of the mica group is XY2 to 3, Z is 4, O is 10, OH F2. Now, okay, so X could be potassium, sodium, barium, calcium, cesium, etc. Whereas Y could be aluminium, magnesium, iron, lithium, chromium, manganese, vanadium, zinc, depending on the specific type of mineral. And Z could be silicon, aluminium, beryllium, and titanium. Here is the end member chemical compositions of rock-forming micas. Now, these are the most common minerals. Actually, there are some more than 28 mica minerals. Among them are the common ones are biotite, muscovite, phlogopite, lepidolite, paragonite, glauconite, etc. etc. Here is the chemical composition for each type of mica. Okay, so of the 28 known species of the mica group, only 6 are common rock-forming minerals. So the most abundant one are muscovite, this one, the whitish silverish variety of the mica group, and then the biotite, which is the black or nearly black variety. These are the two most common mica minerals. The next comes phlogopite and paragonite, and then this is lepidolite. These are also fairly common, and lepidolite is generally pinkish to lilac in color, occurs in lithium bearing pegmatites, while this phlogopite is brown in color, is a typical brown color. Another name which I have not included here, but that's kind of fairly common, which is paragonite, which is macroscopically indistinguishable from muscovite. If you see the hand specimen, you won't be able to distinguish it from the muscovite. The appearance is similar to the muscovite unless you can see it under the microscope. The glauconite is actually a green species that doesn't have the same general macroscopic characteristics as the other micas. It occurs mainly in marine sedimentary sequences. So this kind of indicative of the marine environment. All of these micas except glauconite exhibit easily observable perfect cleavage into flexible sheets. Glauconite, which most often occurs as palette-like grains, has no apparent cleavage. So this is the exception. Here are the beautiful pictures of the mica family. So this one is the most common, muscovite, which you guys, or might be some uh, have seen in the house in ancient times, and a few years until, I mean, even now people use it for as abrak. You might have known this word. They use it for cloths to make them a little bit shinier. This is the common uh, variety of biotite, the dark color one, um, which is found in granite. You can see this is found in granite, which is igneous rock. Along with phosphor and quartz, biotite is present in abundance. This is phlogopite, this is lepidolite, beautiful pinkish lilac color. This is fuchsite, this is also a beautiful color. Margarite and glauconite, which is a green color. It resembles to chlorite as well. Chlorite is so soft that you can even scratch it with your fingernail. Okay, chlorite. The next group is chlorite. So chlorite is the name of a group of common sheet silicate minerals that form during the early stages of metamorphism. So this is the indicative mineral for the early stages of metamorphism. Most chloride minerals are green in color, have a foliated appearance, perfect cleavage, and an oily to soapy feel. They are found in igneous, metamorphic, and sedimentary rocks. Chloride minerals are found in rocks altered during deep burial, plate collisions, hydrothermal activity, or contact metamorphism. They are also found as retrograde minerals in igneous and metamorphic rocks that have been weathered. Rocks that commonly contain abundant chlorite include green schist, phyllite, and chlorite schist. These are actually the metamorphic rocks. Now, chloride minerals have a generalized chemical composition of X, Y, 4 to 6, silicon, aluminum, 4, oxygen 10, hydroxyl, and oxygen 8. The X and Y in this formula represent ions which might include iron, magnesium, manganese, nickel, zinc, aluminum, lithium, titanium. The composition and physical properties of fluorides vary as these ions substitute for one another in solid solutions. Means here in X and Y could be different like iron, magnesium, aluminum, right? So they could be 4 to 6 atoms. Silicon and aluminum could be 4. In this, oxygen could be 10. I mean, for 4 silicon, there will be 10 oxygen atoms. And then the hydroxyl group or water is attached with them. Chloride minerals often form in clay-rich sedimentary rocks that are buried in deep sedimentary basins or subjected to regional metamorphism at a convergent plate boundary. Chloride that forms here is usually associated with biotite, muscovite, garnet, staurolite, and halloysite, or cordierite. Metamorphic rocks rich in chloride might include phyllite and chloride schist. Another environment of chloride mineral formation, I mean how this chloride forms. So the favorable environment for the formation of chloride mineral is oceanic crust descending into subduction zones, where the major tectonic activity takes place. Here, amphiboles, pyroxenes, and micas are altered into chloride. So this could be a product of their alteration, the pyroxene amphiboles and all that. Chloride minerals also form during the hydrothermal metasomatic or contact metasomatism. These chloride minerals are often found in fractured solution cavities or the vesicles of igneous rocks. Their variable chemical composition gives them a range of hardness and specific gravity. This makes them difficult to differentiate in hand specimen because they don't have any diagnostic kind of property, because they don't have a constant um, specific gravity or hardness within the group. So they vary in the hardness and in the specific gravity. So these are the few common minerals which belong to chloride group, which is chloride, clinochlor, pennantite, camosite, etc. So pennantite, here you can see this one is chloride, the beautiful green color, and this is pennantite, the grayish blackish color. This is camosite, which is also pale green. Then clinochlor here mixed with quartz or calcite. This is clinochlor. So that's all for today's class, guys. I hope this would be beneficial for you guys. If you don't understand anything or if you have queries in your mind, please feel free to contact me during the live session as well, or you can contact me anytime through email, through LMS profile, or through SMS. Take care. Have a great day.